you. No more telegraph. Lord have mercy. I'm gonna. Okay, who's still beating the telegraph?
I actually did it.
Okay, no more telegraph, okay?
No, I did it.
I got the examples of that. That's what I did. Oh, I got
I solved it.
Don't call me. I don't know
I
you.
solved it.
You did. I think Yusuf did.
I solved it. Good on you. Solved it. Yeah.
Okay, let's see.
I solved it again. Wait, can I try? Wait.
Yeah, there you go. Okay, if you have not already gotten your Q2 packet off the dining room table, please get it. Clip it in your binder between Q2, Q3. Does everybody have it? Anybody missing there still? There you go. There may be graded stuff at the back of your stack. So I'll read this to you though, but I'm going to change the word. So I'll read it the way she wrote it. So because I hosted the Tinker Day party this year for alumni in Atlanta, and I'm doing it next year, I'm already on the calendar. So I got an actual box of Tinker Day swag, which was probably my favorite part, including the recipe for Tinker Cake, which is closely guarded, so I feel very special. And then they sent me the proclamation. So like where I read October 6th and Suwannee, President Hinton would say today's date, and she'd say at Hollins instead of there. But it says this is what every year, this is what makes it Tinker Day, the official proclamation. So it's the president. By the power vested in me by the great and gracious Board of Trustees of Hollins University, by the memory-filled and mountain-scarred alumna, I love that, and with amused if not skeptical cooperation of the highly degreed, highly tenured, and highly revered Hollins University faculty, and drawing on the blessing of the green and gold mountain goddesses of our campus home, and with deep respect for the mighty tradition stretching back well over 115 years for Hollins students to climb the mountain. And then she says, I, Mary Dana Hinton, president, declare Tinker Day, and then the mountain. Everybody see my friend? So
What's his name?
yeah, you're close. So I cannot remember the man's last name to save my life, but the man who discovered X-rays, first name was Wilhelm. So this is Wilhelm. And I have been on the lookout for anatomical models for years because they're very expensive. A skeleton is somewhere between $500 and $700 generally. Yep, correct anatomical model. But this dude was on Facebook Marketplace for $100, and we had cushion in our budget, so I snagged it. Right, I was like, I'm going to Atlanta, and here I did drive down to Atlanta to some man's house, and it wasn't even his. Like his friend gave it to him to sell, and he's like, my wife wants it out of the garage. Can you please take it? And he had cobwebs in it and stuff, so I cleaned the cobwebs out and tossed him in the van, and then rode home with the skeleton. Right. So that's Wilhelm. But due to his pirate theme for Halloween, I'm calling him One-Eyed Wilhelm because my favorite movie is. And the pirate in that is One-Eyed Willie. One-Eyed Willie, so One-Eyed Wilhelm works, right? And I actually replicated the patch. That's exactly what Willie's patch looks like. Awesome. Okay, well, we'll start since everybody's here. We're about 5 minutes early, but that works. So there will be some Mentimeter stuff today, so have your phones ready. All right. Forces in fluids. So first, we're going to talk fluid pressure. All right. Pressure is the result of what over what, PJ?
Force over an area.
Force over an area, and that is an easy one to remember because if you are to press on something, you're putting the force over the area. So the equation is exactly what you'd expect it to be, force over area. Yeah.
That's why when you're on ice, spread yourself out.
Yeah,
Force
spread
is
yourself out is right if you're on ice, like an icy pond. So to calculate pressure, you're going to do what, Caitlin? Yep, exactly the way it looks with force over pressure. So, I mean, force over area is pressure, same thing. So then the equation would look like that, right? That one makes sense. You don't even have to think about that one. And speed similar because you're used to saying 5 miles per hour. So you can easily do distance over time there, right? Like you can think of that one. But this one is like you actually press and there it is. So pressure is measured as what divided by what, Bailey?
Newton meters squared.
Yes, so it's Newton meters squared and it looks like that. And the unit is a Pascal. So we've got a unit inside of a unit, right? Because a Newton is a unit and then you've got a Newton within a Newton within a Pascal. So we're going to find out some stuff about Pascal in just a sec. I really think Pascal is one of the most fascinating dudes. So what do you call a substance that flows and assumes the shape of its container? Emily, that's a fluid. All right. So what are our two states of matter that are fluid? Yusuf?
Liquid and gas.
Yeah, liquid and gas. All right. That makes a lot of sense, right? So they both assume the shape of their containers and they're considered fluids. Now, let's look. We have a solid in our first beaker here. Does the solid have a fixed shape? Yes or no?
Yeah.
Yes. Does the solid have a fixed volume? Yes or no? Yes. Now, how about the liquid? Does it have a fixed shape?
No.
Correct. It does not. And does it have a fixed volume? Yes, typically speaking. Now, you could put it under a lot of pressure and then you could decrease the volume a little bit, or you could put it in a vacuum and you could increase the volume a little bit, but it's a little bit. So for our purposes, just here on planet Earth, we say it has a fixed volume. So lastly, we have a gas. Fixed shape?
No.
Correct. And how about fixed volume?
No.
No, right. So your gas, you can expand it and shrink it up, pack it down more easily. So water pressure, all right. Water pressure does what as depth does what? All right, Miss Ridley.
Water pressure.
Yes, water pressure increases as the depth increases. Okay, so the pressure in a fluid at any given depth is constant and it's exerted equally in all directions. So that's kind of the point of the Pascal bit today, and we'll talk more about it. But if you think about a syringe, okay? Everybody's seen one and probably used something similar. Even when you're little, sometimes you take medicine with them, right? Like the kind without a needle on it, just the syringe. When you push on the plunger of a syringe, you're only putting pressure on the molecules of the liquid that are right against that plunger, right? But that pressure becomes evenly distributed throughout the liquid, which is what causes it to come out the other end. If you only put pressure on that part right there up against the plunger and it wasn't distributed, it wouldn't move. So then we have to think about atmosphere and altitude. So the weight of Earth's atmosphere that it exerts an average pressure of what? What's the average pressure, Drew? Okay, we're close. So it's 1.01 times 10 to the 5th pascals. I should have made that it didn't work as a superscript, I guess. On the ground at sea level. We also call that something. Do we know what we call that? Do you know what you call it? Close. Do you know, Drew? No, yeah, but no, I mean, what do we call this actual value of 1.01 times 10 to the 5th Pascal on the ground at sea level? Do you know? No, we call it 1 atmosphere, right? Atmospheric pressure. That's the one when you're at sea level, okay? So air pressure decreases as altitude increases. Okay, why? Somebody explain to me. All right, Bailey.
So, like, the higher up you are, the less air pressure you have pushing on you.
Mm-hmm.
So, like, if that's why when on the mountain there's less pressure,
Mhm.
that's why air's thinner, because there's less of it
Yeah.
pushing down.
Right.
Compared to, like, here or at sea level, there's more air pushing down.
Right.
So then you have more pressure on you.
Right. So think of it like this. You've got right now on the top of your head a column of air molecules that goes straight up into the atmosphere. Just imagine it's the same, same diameter of your skull, up it goes, right? Okay, if you're on the top of a mountain, you're a little closer to the edge of that atmosphere. So there's less molecules in that column. So the pressure on you is less. And then if you're at sea level, the pressure on you is more because now your column's taller, right? And when you're in the water, it's the same kind of idea. When you're in the water, you've got, imagine the little column on your head. If you're towards the top of the water, there's less, so there's not as much pressure. But anybody ever, gone down to the bottom of a swimming pool and had to come up because your ears hurt? You had that experience when you go to the bottom? Yeah, you get all that extra pressure. Do you know what scuba divers have to do when they come up? Do you know, Colin?
They have to come up really slowly.
Yeah, why?
Get the exact reason. Yeah. Yeah.
What'd you say, Chloe? I missed it.
Something to do with their blood if they come up too quickly.
Yeah, you're on the right track. What is it, Drew?
Nitrogen bubbles.
Okay, what happens?
Over time your bloodstream.
Yeah, you can get gas. You get gas in your bloodstream, right? I mean, you think about it. There is gas in your blood. There's oxygen, carbon dioxide, and stuff like that in your blood, right? And when you're underwater, way down deep, the pressure on your body is so great that all that stuff is kind of, you good back there? It's more dense, right? And then when you come up, it will expand and form bubbles, which is not good. It's called the bends. It's terrible. Also, their eardrums will rupture if they don't come up slowly, because your eardrums and apparatus in your ears balances the pressure. That's why when you're on an airplane, you're like, trying to pop your ears, right? Because you're trying to balance out the pressure there, equalize. Air pressure always wants to equalize. So here we go. Get your phones. This will be a good one. We're gonna take some guesses about Drew. It's on the guest room bed about Blaise Pascal. If you don't have it, it's okay. You can still guess. Come on up. There you go. Give everybody a minute.
What year was Blaise Pascal born?
That's where we're going. Yep. I think I'm gonna let everybody get here first.
Adorable rat picture.
Oh yeah. Oh yeah. I mean, I worked hard on these rats. All right, who's still getting it? Asher? Everybody else have it? Okay, yeah. Does everybody have a phone except you? Are you the only one without a phone? Here, you use mine. Oh, you don't have one either? Oh no, who's calling me? Don't call me. No, don't call me. You play with one of them. Guess with one of them. And here you go. Do you want to scan it? Okay. Do we all have it? All right, so let me get it started. Okay, here we go. So in what year was Blaise Pascal born? Let's let y'all take some chances. Oh, 0. That's a great year. Take some guesses. Wow, that's a fun year. It's always entertaining. Boy. Got about half of you responded. Got about 9 here, so a little more than half of you. All right, so which of these do we think is closest? Does anybody want to guess, Drew? 2034? Carrot. Carrot's always going to be an answer, isn't it?
I think it's 1652.
1652? All right, well, you would be right. 1623. Okay, so we're talking way back in the day. And isn't he cute? He's adorable. Okay, so where was he born? Okay, some people have already voted.
Wait, no.
Why is the flag right there with him?
I voted.
Yeah, the flag's a clue. But you have to know your flags. If you don't know your flags, it won't help. Should know. And the little beret. So yes, of course, he's French. He was born in Auvergne, France. Sorry. Yep. All right, guys at the back, are you with us? Okay, stay with us. Don't get too far ahead or whatever. So our next one. Okay.
Moo.
How was he educated? By teacher. That's great. Be specific. Do you think he went to university? Was he like, a lot of these scientists were educated with monks and stuff? You know, what do you think he was? University, nice college. Nice college. Give y'all just a second or more.
Yes.
School,
Cool.
3 schools.
Parrot.
Okay,
Oh.
he's a homeschooler.
Yeah.
Yes, his father, so his mother died when he was very young, and his father felt that he and his sisters were too smart for the town school and refused to let them go,
Oh.
which is a little like Edison's mom. Like, you've heard about Edison, right? Edison got kicked out of school because they said they couldn't teach him. They thought he was stupid.
The legend goes.
The legend goes. But the teacher sent a note home to, well, this is what he says too, like Edison himself said it, that the teacher sent a note home and said, let your mother read this, you don't read it. And the note basically said, we can't educate this kid, like he's not there. And so when he asked her what it said, the legend goes that she said to him, it says that you're too smart for that school and you should be home. Very similar. Yes, it did. All right. So at what age do you think he was when he published his first work? At least 2. Carrot's forever going to be the answer. It's my favorite.
At least 2.
At least 2 is a safe bet. It's a very safe bet. Okay. Couple more there. All right. So some of you are underachievers because he was 16 when he published his first work. And it was so profound that the academics of his day thought his father wrote it and put his name on it. Oh, he couldn't have written this. He's just a kid. Okay, so what do you think it was about? I think your options were conic sections, hydraulics, and what are the other ones? Okay. Germ theory. That's right. Ooh, nobody thinks germ theory. Okay. So yeah, it was conic sections. Dude, for real, published a book at 16 about like the volume of chunks of a cone. Like, you take a cone and you find piece. I know, right? Just a little big brain, right? So what were you doing when you're 16? Or what are you doing? Yeah, you publishing conic sections works, people? Get on the ball here. Okay. Egg chicken. So in 1642, he invented something called the Pascaline. What did it do? Air pressure. Good guess. We already know that the unit of pressure is the Pascal, so that's a really good guess. What else do we think? Shredded carrots.
Yeah.
Ate chicken. Invented a something. Yeah, it was a something. Water pressure, air pressure. So the Pascaline looked like that. And it was one of the world's earliest calculators. Actually, for a couple centuries, he was credited with the first ever calculator, this thing. But then we found there was one slightly before him. And he kind of lost that, but he was dead, so it didn't matter. So anyway, that is a calculator. And he invented it to help his dad with his business so he could keep track of things. And then it became kind of a thing that he made a couple different ones and people would buy them, but it wasn't like practical. You know what I mean? Like you just have like a practical thing to roll with. It wasn't practical. It was more like a fancy thing. It wasn't a Honda Odyssey. It was a Ferrari, not practical, but cool. All right. So his most famous work, what's it about? Hydraulics and fluid, music and rhythm, arithmetic, geometry, philosophy and religion, or optical theory and light. I'll give you guys a minute. There's only 80 you responded. There's more than 80 you out there with phones. Take a guess. Then we got another. Okay, so this one's kind of fascinating. So it was about philosophy and religion. This dude, okay, 16, book on conic sections, and then he publishes his most famous work on philosophy and religion. What do you call someone who knows a lot about a lot of things, like a lot of different areas? Somebody who's like, do you know? Close. So somebody who thinks about a lot of things. Somebody who's like educated and, do you know?
Omni.
Oh, yeah, you're going with omni. That's good. So if the word I'm looking for is polymath, A polymath, a good example of an American polymath would be Franklin. Franklin knew a little bit about everything, like he seemed to, right? He knew all kinds of stuff. Yeah, definite polymath. It is also dropped in a lyric in Hamilton. You may have heard it. Hamilton describes himself as a polymath in one of the Hamilton songs. So, and he is pretty good. All right, so here we go now. This book is called Pensée. All right, that was the name of his book. It means thoughts. So it highlighted what we call Pascal's wager. So what do you think it was about? Was it about betting on scientific laws, betting on the existence of God, betting against scientific theories, or betting against the existence of God? So it's this book on philosophy and religion. And you notice he's gambling, right? It's a wager. Ah, he's cute. He's a gambling rat. All right, so you guys are right. It was about on betting on the existence of God. And basically what he said was this, and this is great. This is how a scientist thinks, right? Well, if you're supposed to do A, B, and C because there's a God, all right, let's just say, well, then you're best off doing A, B, and C, because if there is a God, you're good to go. And if there's not, nothing lost. But if you didn't do A, B, and C and there is a God, you're in trouble, right? That was his whole idea. So it was about, weighing your options here. You close cabinet, Drew. So, yeah, it was betting on the existence of God. And it was actually very impactful work. Hey, don't drink in the lab, but he's drinking in the lab. Maybe that's why I came up with all this fun stuff. In his studies of hydrodynamics and hydrostatics, which did he not invent? Syringe, barometer, or hydraulic press?
Hydraulic presses came way after.
You think?
Barometers measure
Air pressure, atmospheric pressure, huh?
Those must have come way after.
So he did not invent the barometer because he used it in his experience and his experiments, can't speak, but he did invent a syringe, or at least he's credited with it, and a hydraulic press. Dude is inventing hydraulic presses, writing about God, just a couple, light things, nothing real heavy, right? All right, what does Pascal's law or Pascal's principle state? Which of these is it? When there's an increase in pressure, there is no increase. When there's an increase in pressure, there's a decrease everywhere else. Or when there's an increase in one point, there's an increase everywhere else. Yeah, y'all got it. Yep. So it's formally stated as when there is an increase in pressure at any point in a confined fluid, there is an equal increase at every other point in the container. So why are we saying confined fluid? Why does that matter? Why are you saying confined fluid? Colin?
because a lot of these things we're talking about hypothetical situations, like
Mm-hmm.
we're talking about speed.
Yeah.
We like to talk about it as if it were in a vacuum.
Mm-hmm. Yeah, that's pretty much it. Yeah, it's pretty good. So yeah, if you're talking about, like we said before, a syringe, right? If you put pressure on the syringe, on the back of the syringe, that gets spread through the whole fluid. And it's confined within that syringe. And if if the end of it's open, then the fluid comes out. But like in this room, like if I go like this, I am pushing air molecules together. I am increasing the pressure right here at this point in the fluid. And it does get distributed. That's how you get like a breeze. Like if I fanned a paper at you enough, you'd get a slight breeze. But in a big space like this, we wouldn't really call it like a confined fluid. Like the air in here is moving all around. All right, so here's a fun one. So he is credited, and this is not one we've already discussed. This is going to be a different one. In 1661, with having designed what was perhaps the first what? We know about the calculator. I know, everybody, you got to invent carrots. This one's going to be very different. And we're going to, highlight how he's quite the polymath with this one, because it's reach far. Think outside the box, because it's way outside the box. A pen, there you go. Hydraulic system, more carrots. Gotta love carrots. Apache attack helicopter. That would be cool. Sewing machine. So, a bus line. Really. Carroza central, which is like a carriage that can contain 5 people. And the whole idea of this carriage moving along, guys, over here, the whole idea of this carriage moving along, people getting out at certain places, other people getting in at certain places, that whole concept of like mass transit where there are stops and people getting on and off. Thank you, Pascal, for your wager on God and your syringe and your calculator and your conic sections paper and your bus line, because these things are, I mean, true polymath, right? That's crazy, all over the place. All right, so he was sick most of his life. So what do you think contributed to his death? Tuberculosis, stomach cancer, convulsions, or all the above?
The above is an answer, you know you gotta get rid of it.
Yeah, that's a good guess. Like, you for real didn't want to live in the 1600s. This was pretty miserable. So yeah, it was everything. It's highly suspected that he had tuberculosis and stomach cancer. He was autopsied. And they did find in his autopsy a brain lesion as well. And the night before he died, he had terrible violent convulsions or seizures, right? Like terrible, scared the heck out of everybody around him. And he was sick like most of his life. So here's a guy who invented all those things we just talked about, had all those crazy and amazing thoughts, and was sick too. Maybe he had a lot of time to sit around and think because he wasn't well. I don't know. So how old do you think he was when he died? 30 something, maybe 30, maybe 39, 40-ish.
Probably the day he died.
Ooh, somebody's got it. Well, these are good, Carrot.
Eric.
Yeah, no.
So somebody was oh yeah, 39. Didn't we have a 39 in there? I thought we did. Yep, there you go, 39. So I was surprised that AI let me do this one because it's real picky. Certain things you put in, it's like, no, I won't do that. It's violent. But it let me put a dead rat in a coffin. I was like, all right, cool. So I was a little surprised. I mean, some of them are creepy because their eyes were open. I was like, no, tell it, please close its eyes. And that was better. This was scary. All right, so where did you find him today? If you wanted to go looking for him, where's Newton? Remember where Newton was?
Yeah.
Westminster Abbey. Yeah, so where would you find Blaise? Is it Notre Dame in Paris? Canterbury in the UK? Saint Etienne du Mont in Paris, Cathedral Basilica Santiago de Compostela in Spain. He was born in France.
Why would he be in Richmond?
Or Richmond. You know, maybe he showed up over here. Richmond was an, early capital. There was stuff going on. Could have been here.
Someone put that in.
I mean, why not? By the way, this one here, Santiago de Compostela. Anybody ever seen the videos of, okay, first off, the thing that in a church you put the incense inside of and you swing it and makes smoke is called a thurible.
Mhm.
You may have seen videos of this because it makes social media frequently. They have a thurible that's no joke, like huge. It's like a wrecking ball. And they have two monks that pull the ropes and it swings through the church. It's massive. Like you could get on it like Miley Cyrus style and just swing. It's huge. So yeah, if you want to see something interesting where you're like, what the heck? Yeah. Like our thurible at church is like this big. I just cleaned it last week. It's this big. This one is massive and it's like brass and heavy. And so, yeah, so he's not there. He is at Saint Etienne du Mont, Paris. What's Etienne du Mont? Anybody know what that means? Anybody take French? Anybody know what Etienne is? It's a name in it. Whoop, in English. We didn't lose it, right? No. Come back. Where did you go? Oh my word. There we go. So yeah, Etienne is Stephen. So Stephen, what do you suppose this is? Dumont. What'd you guess? Nobody wants.
Jared.
What does this word look like? M-O-N-T. Have you seen it anywhere?
Mom.
Saint Stephen of the Mountains. That's right, Saint Stephen of the Mountains. All right, so that's where you would find him. This is his epitaph where he is, I think he's in a wall there, entombed in a wall. And then this is an early sketch of the church from around the time he was alive. And this is what it looks like today. So if you're ever in Paris and you go to Saint Etienne du Mont, you can give Pascal a wave and be like, hey, cool guy, you knew all kinds of craziness. So this is a quick little biography of him. And it kind of sums up what we just went over, but it's good stuff. Well, yeah, why did that? Okay, this is going to be fun. Is this going to be my day? Don't let this be my day.
Blaise Pascal was a 17th century mathematician and
There we go.
philosopher who made great contributions to both fields. You might have heard of Pascal's triangle. He was born on June 19, 1623. His mother died when he was about 3 years old, so his father moved Blaise and his two sisters to Paris and took charge of educating them. Blaise took to math like a fish to water. While other kids were like, I like girls. Pascal was like, I like conic sections. But his dad is worried Blaise would reject the classes, so he bans math from their studies. Blaise took to studying geometry behind his dad's back and made up a lot of his own geometry terms. As a teenager, he started working on calculating machines, known as Pascal's calculators. Over 13 years, he built 20 machines and 50 prototypes, including one of the first mechanical calculators. But it wasn't a huge commercial success. It was cumbersome and it was really expensive. It became more of a status symbol for the rich than an actual machine. Pascal is also credited with coming up with Pascal's triangle. It's basically an addition pyramid. Each number equals the sum of the two numbers above it. This creates patterns along the diagonals and the rows and can be used to solve things like probability, combinations, and exponents. Outside of math, he dabbled in the sciences, invented the hydraulic press and the syringe. Pascal may have been a man of science, but his most famous work was entirely unscientific. He had one of the most unique perspectives on religion and faith, particularly the belief in God. Pascal was by no means the first scientist to question or attempt to prove or disprove the existence of God, but his take was unique in its pragmatism. The way he saw it, like a mathematician, the odds of success were what mattered. If you do believe in God and he exists, you win. If he doesn't, well, nothing lost, nothing gained. So Pascal argued, bet on God. You have nothing to lose. This hedging your bets approach to religion became known as Pascal's wager, and it opened up an entirely new way of thinking about religion. Pascal viewed the world in terms of maximizing benefits in return. So even if you're not a religious person or you take issue with Pascal's wager, you can't deny that Pascal ushered in a new school of religious and philosophical thought. Pascal continued to write on religion and philosophy until 1662, when he died from a stomach tumor at just 39.
39. So, you know, when you're thinking, have I done enough with my life? When you're 16, you haven't even written a book yet. Come on. And then when you're, 47 and you pass 39 and you're like, wow, this is one of those people that, historically we look back on and go, good gracious, what huge contributions, what a great mind.
What am I doing?
Right? Yeah, true. Yeah. I mean, if he's wealthy enough and he didn't have to go work in a field all day or whatever, then you have time to think. And he's sick. So, maybe.
He couldn't go anywhere.
Right.
Stay home.
Right. Exactly. So transmitting pressure in fluid. So we know that we have pressure can be applied to fluid. So how does it transmit? So a change in pressure at any point in a fluid is transmitted equally and unchanged in all directions throughout the fluid. So that's Pascal's principle or Pascal's law pretty much. So if the fluid is not fully contained, increase in pressure on the fluid creates what? What do we call that? And it moves the fluid from one place to another. What are we looking for here? All right, Yusuf. Yeah. It's a force pump. It is a type of hydraulic system. So this is interesting. So I don't think that one was directly in your book, but great example. Last week, balloon rockets, right? Liam lived up there. Everybody seemed to have a good time. Liam just never came down. He hung out up there. I think he popped every balloon we had. Everybody had a good time, right? All right. So you're blowing up the balloon. Poof, poof, poof. All right. You've stretched the latex out and all the air inside is under a lot of pressure now, right? Because the latex is stretched and you've put lungs full of air into this space. Okay. When you let it go, you guys noticed that it moved, right? It had an equal and opposite reaction. But the reason that it moved, what's the reason? Why did it do that? Why did the air come back out, Drew?
Because the balloon is pushing down on the air with its elastic.
Yep.
You let go of it, it just pushes all the air out.
Right. So that's part of it. That's part of it. Part of it is that the balloon, now we've stretched it. And that particular, that matter wants to be in its more comfortable state. So it kind of wants to shrink itself back down. Yeah. So really the other thing is the air is trying to equalize or balance pressure. So when you let the balloon go, we were talking about you and the balloons last week, man. When you let the balloon go, the air inside is trying to equalize with the air pressure outside. So the air is higher pressure in the balloon, so it comes out of the balloon. So that's the whole thing when it's equalizing. When you're on a plane, what happens when you drive up high on a mountain or when you're on a plane with your ears? Yeah, well, you have to pop them, right? You can feel the pressure and you ever do that. People do weird things, blowing, puffing in their nose. And that's equalizing pressure because the pressure on the inside is now greater than the pressure outside. So you're trying to stretch it a little bit and there's some openings in there and it spreads it out. So yeah, so always trying to equalize. Pressure is always trying to equalize. And think about spray cans, okay? Like spray paint, bug spray. Yeah, anything with the aerosol spray. Like what's going on there? When you push the little button at the top, what's happening? Bailey.
Pressurized air pushes the.
Right. And why is it coming out? Like
It's trying to equalize.
it's trying to equalize. There you go. So it's just trying to equalize. So that air inside is under pressure, which is why, like, it says do not put near flame because there's a lot of stuff in there. Yeah. And if it goes kaboom, it'll go kaboom, right? All right. So hydraulic systems are designed and they take advantage of what? Milo. Yeah. And what do we call this whole law? We're just talking about, yeah, Pascal's principle or Pascal's law. So hydraulic system multiplies force by applying that force to a small surface area and increasing the pressure that's then transmitted to another part of the confined fluid, which pushes on a larger surface area. So this is how, anybody ever been to like the dealership or a mechanic and then watched your car get lifted on one of those hydraulic lifts? Those are pretty cool. So my dad works on cars, right? He has a car shop. That's what he does, is alignment, brake, and balance. And we don't have lifts, we have pits. So we went the other way. We dug a hole in the ground and you drive up on the rack and you go down on the hole and work up. But a lot of people have these big hydraulic lifts and they lift the cars way up in the air. So hydraulic systems are frequently used in industrial applications as well as in nature. So there is a water vascular system in some echinoderms. What's an echinoderm? Who remembers? All right. Oh, James. Not jellyfish. But you're close. It is marine. They are marine typically. Colin wants to help you. What? Sea stars. Okay, there you go. Sea stars, sea urchins, sea cucumbers. These are echinoderms. So echinoderm translates to spiny skin. Okay, and they, like sea stars are a great example. They actually use a hydraulic system to move. It's called a water vascular system. If you did biology, you might remember that. And that's how they move around. And it's pretty wild. Like they push water from one part of their body to move their arms. Yeah.
Can you go back to the other one?
Yeah.
No, like it has periods instead of commas.
No, they're actually commas. They're just very, very small. See it?
What?
See it?
On that thing, it's fine.
You tried. You failed. Anyway. Okay. So here we go. So according to whose principle again? Who is it? Everybody just say it. Yes. Oh, wrong. Bernoulli. I love it. Okay. So let's talk about Bernoulli. Okay. I need a guinea pig. Who's going to be my guinea pig? I need a guinea pig.
Do I get coins?
Oh, okay. I'm gonna pick Liam since you had the thing with the balloons. All right, Liam. This is a giant long bag. I'll open it up, make sure it's all open for you. Big long bag. Okay, so you and I are gonna compete. You can blow it up the fastest. There's your bag. You can go ahead and start. We'll get mine all straightened out. Yeah. No, tell him what to do. No, don't tell him. Don't tell him. Cheater. You're cheating. Yeah, he's blowing. No, screw. All right, so he's blowing, right?
Like that?
No, like that.
Oh, okay. Oh.
Oh. Getting there, Liam. You're getting in there. Yeah. Good. There you go. All right. So that was a spot on, perfect demonstration, Bernoulli's principle. Did it work when he was pumping it?
Nope.
No, it's taken forever, right? Wasn't going anywhere. So Bernoulli's principle is that as the speed of a fluid increases, the pressure within the fluid decreases. So how did this work? What happened? Jordan.
The air was going really fast into the bag,
Mm-hmm.
made the air expand and fill out more space.
There you go. So yeah, it was filling up the bag because we weren't blowing directly into it. We were blowing in front of it, and we were creating basically this little diagram here. So why doesn't it work if you, why can't you do that with a balloon?
Small,
Smaller, what do you think, Yusuf?
elastic.
Yeah, it's elastic, right? You have to fight the elastic on the latex on a balloon. Yes, Drew?
It does work on a balloon. It just won't get very far.
Yeah, it won't get very far. Exactly, because
It'll get no.
because you need pressure from your lungs and your mouth to force the air into that balloon. Okay, so Bernoulli's principle works for all kinds of things, and we're going to talk about it in a minute. But first, we're going to take some guesses on Bernoulli. You don't need the Mentimeter, I don't think. Yeah, but we're still going to guess. So February 8th, 1700. So the 27th of March, 1782. So he was 82. That's old for the 1700s. Like, he's a sage. You go ask him questions about life because he knows everything. All right. So where do you think he was from? Let's see. Raise hands for Switzerland. Vote. Ooh, raise hands for an Italy. Vote. Yeah, with that name, Bernoulli, you would think, but no, he's from Switzerland. Yeah. He's hanging out with the cheese. No pasta for you. You get cheese. Right, right. Okay, so his dad, what does his dad want him to study, writing or business?
Business.
What do you think? Writing, vote for writing. Oh, vote for business. All right, you guys are good. His dad wanted, why would your dad want you to study business? Yes,
When was he born again?
1700, is that what it said?
No, wait, what month?
February 8th.
That's my birthday.
What do you know? You share a birthday with Bernoulli. So yes, business. Why would your parent want you to study business?
Money.
Yeah, that means they don't have to pay for you anymore, right? You make money, they don't have to pay for you. Yep, yep. Go buy carrots, go own carrots. Thank you. I'm not paying for you your whole life. That's right. All right. So what did he actually study to become? An innkeeper or a doctor? So who votes for doctor? All right. Who votes for innkeeper? Oh, it's a good split. Became a doctor. His dad was a little disappointed,
Why?
right? Right. I don't know if he was.
Disappointed because his son didn't become exactly what he wanted to be.
So many parents are like this.
So doctors didn't get paid as much as they.
That's true. Yeah. So, and the other thing about doctors, like you think of doctors today as surgeons, but in the 1700s and several centuries around it, surgeons were barbers. Did you know that?
Yeah.
The barbers were the surgeons and the dentists, right? Yep. So if you needed a tooth pulled, the barber did it. You didn't go to a dentist because there really wasn't, you know. And if you were if you had a limb that was rotten off, like your finger got gangrene, you went to the barber and the barber removed it, not the doctor.
Without anesthesia.
Oh yeah, without anesthesia. They just fill you up with some rum and here's some rum, here's a stick and some leather, bite down, enjoy. Woo.
All the blood out your body since bad blood.
Yeah, they did do that a lot too. Yeah, there are some fascinating historical medical procedures. Actually, when I was about 12, I worked as a tour guide in a 1700s house in Virginia Beach. It was a really old house. And we had to dress in period costumes. My grandmother had to like sew a bonnet and all this business for me. We had to learn how to play with the tools so I can do Jacob's ladder and hoops and all these things that I learned to do. But we had to act as if we were the children. So it was a historical interpretation. So it was me and two of my friends. And we would, you know, just be part of the scenery, or we would give the tour. And the thing I remember about the medical stuff is if you were sick, the cure was to give you 3 pills made of deer dung and turpentine. Oh.
Yeah, but like.
And then they would bleed you 3 cups. So either they would slice you and let you bleed, or they put leeches. Yeah, 3 cups is a lot. That's a lot. So yeah. Yeah. Yeah, and leeches. And by the way, if you ever want to buy me something weird and you have like won the lottery, because they're about $500 a piece, but I for real want one because I like, I like weird stuff. There are some still antique excoriators from like Civil War period. And it's a usually they're brass. It's a box like this. And it has a switch on the side that is spring loaded. And there are little like round, like circular blades and little slots in the bottom. So they would put it on your arm, hit the switch, and the blades would go, and they come out the little slots and they'd slice you in multiple places so that they could bleed you. But they're just really cool things. So I think they're really neat. So what was he best known for working with? Numbers or insects? Who votes numbers? And who votes insects? Good guesses all the way around. Numbers. It's a numbers guy. Right? I know. I had to come up with something weird. All right, so he made one of the first attempts to analyze the results of smallpox inoculation efforts or preserving food by canning. Ooh, this is fun. We know he was a doctor, so either could be good. So who votes for smallpox inoculations? Ridley, Bailey, Emily, Jordan. Who votes for canning food? Smallpox. How did they do smallpox inoculations in the 1700s? Does anybody know? Do you know, Chloe? You're right. Exactly what they did. They would take pus and lymph and fluid out of the pox of people who had smallpox. And then they would come up to you and they'd scrape and stick a little hole of it and jam it in your body. Yes. You know what? Jenner did this, yeah, the vaccine. He analyzed the results of the inoculation efforts. Like, are they working? Is this actually working?
What do you use cowpox?
Yeah, cowpox. Yeah, they use cowpox too if they couldn't, yeah. Because cowpox and smallpox are a similar virus. So yeah, so next time you're at the doctor and you complain about a shot being like a quick needle, just remember you could have had somebody else's pus or a cowpox pus from a cow jammed all up in you. That's not fun. Cool. But hey, they did work. So Bernoullis, these are an interesting family. It's not just our Daniel, it's the whole crew.
If you've ever taken a science or math class, you're probably used to lots of things being named after the same people. There are hundreds of principles and theorems and equations named after superstars like Euler and Laplace and Gauss, so it might not seem all that weird to learn about Bernoulli's Berkistik-Crone solution, Bernoulli's equation in fluid dynamics, and the Bernoulli probability distribution. And you would assume that they're all named after the same person, but they're not. In the 17th and 18th century, there were actually 8 mathematically gifted Bernoullis from 3 generations of the same family, but 3 of the Bernoullis really stood out: Jacob, Johann, and Daniel. They were all descendants of Nicholas Bernoulli, who was born in 1623. Nicholas had 3 sons, who were named Jacob, Nicholas after himself, and Johann. The younger Nicholas became a painter and a city official, but his brothers were famous mathematicians. Jacob, the oldest, solved a number of early calculus problems that are still taught in schools today, but Jacob's most important discoveries were in probability. He was the first person to prove something called the law of large numbers, and he came up with what's now known as the Bernoulli distribution. Both are ways of predicting a series of random events. Say you roll a 6-sided die a bunch of times in a row. If you roll the die, say 3 times, you might get a 1, a 4, and a 6. You might also roll 3 2s. It's random. But the law of large numbers says that as you roll the die more times, the average of all the numbers you rolled will get closer and closer to 3.5, the average of all possible rolls. That's because after a lot of rolls, say 1,000, you'll have rolled each number roughly the same amount of times. So the average of all of your rolls will be very close to 3.5. Jacob Bernoulli was the first person to officially prove this, and it became one of the early fundamental concepts of probability theory. The Bernoulli distribution is a similar idea that applies the law of large numbers to something like a coin flip, where there are only 2 possible outcomes. Jacob also discovered a famous mathematical constant, E, which is used all the time in math and sciences. It can describe anything that grows continuously, from bacteria to a bank account that's accumulating interest. Jacob's younger brother, Johann, was also interested in math. In 1696, he proposed a fun problem for the world's mathematicians. What's the fastest path for a ball to follow if it rolls in a track between 2 points? He called it the Berkistik-Crone problem, from the Greek words for shortest and time. You might assume that the fastest path would be a straight line, and a straight line is the shortest path. but it's not the fastest one. The fastest path for a ball to roll between 2 points is actually kind of a stretched out piece of circle called a cycloid, because the weight of gravity makes a ball accelerate. Galileo and a few others had figured this out on a conceptual level, but Johann used calculus to prove it. Jacob then found his own solution, laying the foundation for a whole new branch of calculus while he was at it. Johann also discovered ways of finding an answer to things like 0 divided by 0 and infinity divided by infinity. His method is now known as L'Hopital's rule, but all Guillaume de L'Hopital did was publish his notes from Johann's calculus lectures. Johann's 3 sons were all mathematicians as well, but probably the most influential one was Daniel. One of the things that's named after him is Bernoulli's principle, a concept in fluid dynamics that describes the relationship between pressure and speed in a moving fluid. Bernoulli's principle is part of why airplanes fly, the air on the top of the wings going faster than the air on the bottom. In physics, Daniel worked with the famous Euler to develop the Euler-Bernoulli beam theory, which describes the way forces make strong rods bend. Euler-Bernoulli beam theory and the physics based on it are still super useful for engineers these days. There are, of course, beams in our bridges and buildings. So we should understand them. Daniel also developed new mathematical methods of measuring risk, and he was one of the first physicists to study the behavior of gases. Part of the reason the Bernoullis were so successful was that they were in the right place at the right time. Newton and Leibniz had just invented calculus, so there was this powerful new technique for describing the universe. But the Bernoullis were also talented mathematicians and scientists who used the tools they had to uncover all kinds of new things about the universe, which is why these days their names are all over our science and math textbooks, even if it is sometimes hard to keep track of which Bernoulli did what. Thanks for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support this show,
I can think of another family, composers, that have a similar thing where you have to figure out which one it is. Do you know who? The Bachs. There's more than one Bach. Usually it's JS that you're thinking of, Johann Sebastian, but there are multiple Bachs. Yeah. So sometimes if somebody says, oh, it's by Bach, it's like, which Bach? It's kind of like which Bernoulli. Okay, so Bernoulli principle. You can see this with spray bottles, like the kind you use in lawns, the kind you hook up to your hose. You seen those, like the pump bottle, you hook it up to the hose and you spray, right? And then also atomizers. So this is an atomizer. You may have seen them, like sometimes they're in old cartoons or whatever, but it's usually they're like perfume bottles when you see them. It's like a pretty little perfume bottle and has a little tube and then a little squeezy bulb at the end, and you squeeze the little bulb and stuff comes out. And any of the spray bottles that we use to clean that have the tube that goes down inside, just like this, just like the kind you use to clean your kitchen counter. The idea is that the air jet that comes out of this horizontal cane causes the depression of the vertical cane. They're using cane instead of tube, and I don't know why, which will draw liquid from the small bottle and then disperse it in tiny drops. So atomizers, spray bottles, all this stuff function similarly, using air pumped as fast moving fluid, reduces the pressure at the top of the straw, draws the liquid up. Yep, and he is spraying flowers, and I can't believe AI let me do that one. That's impressive. Yes, sir.
At the top it says Bernoulli principle. It doesn't have the S.
Okay, there you go. All right, you found one. Wings and lift. Okay, lift. What is this here? A what force created by the difference between what and what? All right, who wants to do it for me? Let's see, who hasn't gone yet? Oh, Asher, you haven't gone. You're the only one that hasn't said anything. You know any of these? You want to take a guess? You can always just say carrot. No, just kidding. Don't say carrot. He's looking. Okay, drag is a good one. Anybody else want to throw a guess at it? Chloe. Upward. All right, so yeah, we have an upward force created by the difference between the what pressure on top, Colin?
Low pressure.
Low pressure on the top of the wing, and what kind of pressure then beneath it, Lucas?
High.
High. Okay, so this is a very simplified diagram of how a wing works, but it's not entirely why airplanes fly. It's actually more complicated. This is the most basic way. So if you ever been in a car, if you haven't, do it today. It's nice weather. But you put your hand out like this.
No.
And if you put your hand slightly tilted, you feel that the air push it down if you're driving in the car. Yeah. And then you do like this. You ever done like this and feel the air move around? And if you curve it a little, yeah, it's cool to do. Hand off the window. Woo! Okay, so the idea here is that as the air comes towards the front of this wing, which is curved, this can be a bird wing or an airplane wing, that the air going over the top has a longer path than the air on the bottom, which causes the air molecules to spread out because it's a longer path. And then the ones underneath are closer together, so the pressure's higher underneath and it pushes it up. Caitlin.
Why does he have an airplane? Is he like a time traveler or something?
He's playing with it. I don't know. Yeah, he's a time traveler. He also has a drawing of something on his bed. I got in trouble for that, unless it's his bed. So this is the more accurate description of why planes fly.
By 1917, Albert Einstein had explained the relationship between space and time. But that year, he designed a flawed airplane wing. His attempt was based on an incomplete theory of flight. Indeed, insufficient and inaccurate explanations still circulate today. So, where did Einstein go wrong? And how do planes fly? Though we don't always think of it this way, air is a fluid medium. It's just less dense than liquids like water. Things that are lighter than air are buoyant within it, while heavier objects require an upward force called lift to stay aloft. For planes, this force is mostly generated by the wings. One especially pervasive false description of lift is the longer path or equal transit time explanation. It states that air molecules traveling over the top of a curved wing cover a longer distance than those traveling underneath. For the air molecules above to reach the wing's trailing edge in the same instance as those that split off and went below, air must travel faster above, creating a pocket of lower pressure that lifts the plane. This explanation has been thoroughly debunked. Air molecules flowing above and below the wing don't need to meet back up. In reality, the air traveling above pushes the wing's trailing edge faster than
Oh.
to get a sense of
Buffer for a minute. Don't be crazy. Okay, let's try that again.
faster than the air beneath. To get a sense of how lift is actually generated, let's simulate an airplane wing in motion. As it moves forward, the wing affects the movement of the air around it. As air meets the wing's solid surface, a thin layer sticks to the wing. This layer pulls the surrounding air with it. The air splits into pathways above and below the wing, following the wing's contour. As the air that's routed above makes its way around the nose of the wing, it experiences centripetal acceleration, the force you also feel in a sharply turning car. The air above therefore gathers more speed than the air traveling below. This increased speed is coupled with a decrease in pressure above the wing, which pulls even more air across the wing's upper surface. The air flowing across the lower surface, meanwhile, experiences less of a change in direction and speed. The pressure across the wing's lower surface is thus higher than that above the upper surface. This pressure difference results in the upwards force of lift. The faster the plane travels, the greater the pressure difference, and the greater that force. Once it overcomes the downward force of gravity, the plane takes off. Air flows smoothly around curved wings, but a wing's curvature is not the cause of lift. In fact, a flat wing that's tilted upwards can also create lift, as long as the air bends around it, contributing to and reinforcing the pressure difference. Meanwhile, having a wing that's too curved or steeply angled can be disastrous. The airflow above may detach from the wing and become turbulent. This is probably what happened with Einstein's wing design, nicknamed the cat's back. By increasing the wing's curvature, Einstein thought it would generate more lift, but one test pilot reported that the plane wobbled like a pregnant duck in flight. Our explanation is still a simplified description of this nuanced, complex process. Other factors, like the air that's flowing meters beyond the wing's surface, being swept up, then down, as well as air vortices formed at the wing's tips, all influence lift. And while experts agree that the pressure difference generates lift, their explanations for how can vary. Some might emphasize the air's behavior at the wing's surface, others the upward force created as the air is deflected downwards. However, there's no controversy when it comes to the math. Engineers use a set of formulas called the Navier-Stokes equations to precisely model air's flow around a wing and detail how lift is generated. More than a century after Einstein's foray into aeronautics, lift retains its reputation as a confounding concept. But when it feels like it's all going to come crashing down, remember, it's just the physics of fluid in motion. This video was made possible.
So you probably
with
heard
support
the
from Henriette.
bit before about, you know, longer path, the longer path argument, which that's been like the standard discussion. And it is in most textbooks. I think it's in yours too, the longer path idea, but it is more complex than that. That's why the flat wing works if you just tilt it. That's why your hand works on the outside of a car if you do this, right? You get that whole impact with your hand. All right, so then what causes turbulence when you're on a plane? Anybody ever been on a plane with turbulence? Do you know? Okay. Air pressure differences. So if you've ever been on a plane and experienced turbulence, it can be a little scary. It scares me. I don't like it, even though I know it's totally normal. It still freaks me out. And pilots usually try and fly around those areas, but this is a really good. This is just kind of like additional to what we're learning, but it's really good.
Turbulence is the wind hitting the nose.
This is Captain Stuart Walker. After more than 30 years of flying, he knows a lot about turbulence, and there's more than one type.
We've actually got the winds coming from all different directions of the airplane.
He's here to explain the main types of turbulence, how they impact your flight, and what he and you can do to get the smoothest ride.
There's many types of turbulence that you can find out when we're flying, but the four main types are clear air turbulence, thermal turbulence, mechanical turbulence, and wake turbulence. Clear air turbulence is exactly that. It's clear, it's there, it's turbulent.
Meaning it may look clear outside your window, then the plane starts to shake.
Ideally, if we're traveling, we've got a nice tailwind, and if we've got the jet on our tail, we might have 150 knots of extra ground speed just because of that tailwind. But if the jet stream veers off, I'm going to lose some of that tailwind. And as I do, I change the dynamics of the airplane, and basically I can get a rocking motion, or I can get a large pitch up if it's a shear from another crossing wind.
So what's happening here has a lot to do with jet streams, those invisible rivers of air that encircle the globe.
And when they are bent and turned, they create shears in the air, and those pockets of shear are where we're finding that clear air turbulence. We've got 150 knots off the left wing, and all of a sudden it's shifting to a tailwind. We're expecting that it's probably going to have a little bit of a shear.
But clear air turbulence is tough to predict, Walker says. Pilots rely on modeling, graphical displays on board, and information from dispatchers to try to avoid turbulent areas.
The good news about clear air turbulence, though, is it typically does not last but a couple thousand feet. So if we just descend a couple thousand or climb a couple thousand, we can usually fly out of some of that rough air. Thermal turbulence is just the opposite of clear air turbulence. We can see it.
That's because it's caused by rising warm air, or thermals, which can create cloud. Cumulonimbus clouds, the kind that carry thunderstorms, are the biggest concern. Typically, planes fly over most of the weather, but clouds can sometimes tower up into a plane's cruising altitude.
So if our aircraft encountered, for some reason, flew into an area that had those towering clouds, what we would expect is we've got a lot of those vertical shafts either coming up or down. And so we're going to get some pretty violent movement on our aircraft. Not only that, but we might have those hailstones that might damage the aircraft or our engines. So for that reason, it's always best to turn around and fly around the weather.
But dispatchers try to stop this scenario before it even happens by giving pilots a detailed flight plan, which contains in it a route that should avoid these weather systems.
When I get the flight plan, I've got some of the same tools in my cockpit. when the weather changes and moves and shifts, I get the real-time information. And when I get that, I'm able to make much better decisions about my route of flight or my altitude.
But don't worry if you fly through clouds on your next flight.
I get a lot of people sometimes ask, do you just avoid all the clouds? And the answer is no. When we have nice strata cloud, those clouds, if we fly through those, you probably wouldn't even notice. Mechanical turbulence has kind of a funny name, but it's exactly that. There's something mechanically in the way of that wind that's blowing. Down in lower altitudes, it might be trees, it might be buildings, it might be hills. Up at higher altitudes, it could be something a lot more than just the trees and the hills. It could be the Rocky Mountains.
The Rockies can create what's called mountain wave. It happens when air blows over the mountains and falls down the other side, creating road to air, or then cut into the street, sometimes hundreds of miles from the mountain.
Buffer.
Intriguing.
Yeah, no.
If we're flying and we've got the Rockies over here and we've got that strong wind, with those rotors as they come up and they impact my aircraft, sometimes I'm going to see an increase in performance and then a decrease in performance of the aircraft. It might cause my aircraft to pitch up slightly and then back down. Typically, they're not as violent if I'm hitting them head on, but if I'm hitting from the side, sometimes it can give you a good rocking motion.
To try to avoid these situations, Walker says he communicates with air traffic control to learn of any reports of mountain waves before entering mountainous airspace.
As a pilot, we're always concerned about mountain wave because just like clear air turbulence, it can just all of a sudden be there and not there. But if we can fly at a lower altitude, we can avoid some of those rotors, or we can sometimes fly above those that altitude and avoid them as well. Wing turbulence is something that we encounter when we come in for landing. It's something that comes naturally off of our wings. It's a byproduct of the lift on the wings. As that airflow directs the wind over and around, off the wingtip, we get these vortices that come off the wing on both wings. And so you can actually see them trailing off at times.
Think of it like the wake off of a boat. The vortices of air coming off the plane's wings tend to dissipate out from the aircraft.
If we're following too closely behind another aircraft, that wake, instead of falling and dissipating down here, it stays active for a couple minutes and it can be blown back into our course. So if we're the aircraft following, we might encounter that wake turbulence and we get basically a little bit of a rocking.
How much rocking depends on the plane in front. Typically, larger aircraft produce more wake. Still, this doesn't worry Walker much.
The good news about wake turbulence is that all we have to do is adjust a couple, 50 feet, a little bit left or right, and we're out of it.
Though pilots are working to keep the plane flying smoothly, Walker does have a few tips for flyers looking for the calmest ride. First, where you sit.
If you are one of those that are fearful of turbulence, you know that actually sitting over the wing, maybe further to the forward part of the cabin, is going to be a slightly better ride than the back of the bus.
Second, when you fly.
Maybe book it in the morning. Typically in the morning, you don't have quite the heating and you don't have that thermal turbulence that we were talking about.
And as every pre-flight announcement says, keep your seatbelt fastened. You never know when you may experience rough air.
So as you can tell, a little more complicated than the simple model of the longer path. And then you get, come on, change the, hello. Then you get the whole, this won't go, there we go. You get the whole issue with, oh, fun. This is gonna make me crazy today. Sorry. But you get the whole issue with changing. Yeah, I got lots of, those are logos. I don't know why it's doing that for me. But anyway, so yeah, so obviously fluid dynamics are going to matter if you're in a submarine, if you're in an airplane, anywhere where you've got fluid. I don't need to go there. I need to go here. Stupid. So, okay, next week. I don't know if there's, I think that's the last slide, but I want to double check. So next week, we have Halloween at the same time as lab, right? As class. So you're going to want to, don't go shove them around yet. You're going to want to, if you want to wear a costume, like I said, totally fine, but be sure that it's not distracting and it's not going to get in the way. You will be working with water. So you're gonna want, hello, everything opened up. You're gonna want to be able to get wet, and you're gonna be working with water. You may get up to your elbows in water next week. Hold on, let me make sure that we got, yeah, that was the last one. Okay, so we still have some time because we started early since we wrapped up lab, and that's fine. So what you should do right now for the next few minutes, unless you've driven yourself and you can scoot early, what you should do is take the time to make sure that your lab is complete. Put at the end of lesson 10. And then you've got lesson 12 forward. Now, lesson 12 forward, there are no more homework assignments in the binder because I only put those in the binder as a, that was our backup when the whole Teacheries thing happened. We put some homework assignments in the binder that you could do on paper if we weren't able to use Teacheries, but we are now, so they're all going to be there. Their unit 4 and unit 5 are in Q2, but Q2 is not very long. It's lesson 12, 13, 14, 15, 16 is review, 17 is midterms. It's a very, very short quarter. It's not really technically a quarter calendar wise, but I would have had to chop up forces and it didn't make sense. So we just kind of moved it out. Anybody have any questions about anything? Yes, Miss Chloe.
Lab teams for the final.
I haven't gotten to that yet, but I will say this. If I will consider, if you privately message me or email me or text me, if there's somebody you would like to work with, and if there's somebody that you like really have had an issue with, I don't think anybody in this room has, but in case there is, you can always, tell me who that is. You don't tell everybody else. And I will try to have that, shored up by midterms, because I want you to be able to start planning for that. That's going to be, if you guys notice, that's going to run, hang on, I move this real quick. I'll show you. So if you look at your syllabus, which everybody should have right there in front of them, because you have your binder. But if you look at your syllabus, you'll see that the last couple weeks of class, the lab for those is, make sure I got this real quick. Sorry. I can't talk and read at the same time. It's just not something I can do. So you'll notice that the lab for those last couple weeks is going to be all building, right? You have lots of time to build. So I will let you know ahead of time who your lab teams are, because you're going to want the opportunity to start planning. Why is everything so slow today? Everything I click, just there we go. Maybe. Oh, that's fun. So little you can't see it. All right, so let's see, that's the last one. All right, so lessons, where does it start? Okay, so you have, we end up with chemistry, basically. We have a little bit of chemistry at the end of physical science, which is perfect because it leads into next year's class, which is chemistry, right? So the last lab that we have before we hit the Rube Goldberg is the lesson 29, which is mid-April. And that's periodic table battleship, which is fun. Then we move into Rube Goldberg machine project. And you'll be doing that lesson 30, 31, 32, and then 30, that should say 33. I have to fix that, don't I? The last day of class after exams, we do the Rube Goldberg competition. So you have your finals, and then we go outside and we do the Rube Goldberg. Now you have in your binder right now, your lesson 17, which is our midterms day. If you look at that, you'll see that it has the time for arrival, which is earlier than usual. You can arrive as early as, I think it says 10. Miss Jackie has people that can come even earlier than that. If you have Miss Jackie, which is all three of you are here, you'll do Miss Jackie's exam first, and then you'll do mine second. It is a written exam. If you've not done one with me, which is about half of you, it's on paper. It's a written exam where you have to, fill in a circle or write an answer, or sometimes you have to diagram something. So it's on paper, but we have lots of review beforehand. You'll know exactly what to expect. Lots of review. The week before, we're playing Jeopardy, Team Jeopardy, with the answers, which is always fun, right? And then we're watching a movie after we complete that midterm. Does anybody see what the movie is? Do you look? Say it. October Sky. Okay, October Sky is cool, and I have a description of it on the back page. Whoop. Has anybody seen it before? Anybody ever seen it? Yeah? Yeah? It's really good. It's about rocketry, and it's fun. So, anyway, there's definite use of a lot of the stuff we've talked about as far as motion paths, force, all that's involved. So, anybody have questions about next week or about moving into Q2? Yes.
Are we going to change teams?
You will change lab teams beginning Q2, and then you will change them again Q3 and Q4. Anybody else? Questions, anything? So if you drove yourself, you can scoot a little early today since we started a little early. And if you didn't, you can just hang. I have coinage, and coinage. And happy Tinker Day. I think everybody is getting their full bonus points because y'all all dressed up and we're good to go. Outstanding. Thank you, Emily. So, happy Tinker Day. Woo. Very good, very good.
You want a point?
Yay. You got one, you got one. There you go. Good deal, good deal.
I got one of the smallest.
Oh, it doesn't matter. They all work the same, right?
Yeah,
Thank goodness we have it set. They all work the same, so it doesn't matter.
So we don't have to hike a mountain.
You don't have to hike them out because it was too close. Here you go.
So only my mom let me have my phone and graded my math papers yesterday. Like I told her she never should do. Because I want my phone back and I haven't had it in a week. And I could tell her she doesn't need to buy Krispy Kreme donuts.
That's so funny. Well, she should know because it went out this morning, messages and everything.
Yeah, but she was like, so we're hiking Sonny Mountain between the 2 hours between I get home and then
Yeah, go for it. Go for it. Why not? I used to do it when we were little. We went every year. Yeah.
And I exchanged my phone for
How about it? Thank you all for cleaning up that today. You guys, great. You got stuff done. Next week, we're going to do. We will have big fish tanks full of water. You have your big one. Yeah, James, you're right. Yeah, because the dice went situation, right? Yeah. Very cool though. Awesome fun.
There might be like
Yeah, probably the ones with the deep juice or whatever. There, that's Tinker Day. And that's Tinker Day, that's Tinker Day, today. Let's leave it all today though. Tinker Day. Back when I had a dot maker.
The dot maker's food.
Yeah, really. Oh, wow. Huh? It's printed like if you look, it's these little spots, but when you ran your paper through it, it had like strips on the side that were perforated, so you could tear them off. But the paper had little holes, so it was like a gear with pushing the hole through the crack. But they went a terrible noise. It was like, wake up everybody in the hall. They were so loud. The ring knife, all the good fun stuff. What? You get whatever email you're waiting for?
No, our resident engineer was supposed to be expired, his contract was supposed to expire today,
Oh,
which is not good.
yeah, that's not good.
I found the brushing tool, but I never.
Oh, cool. Where is it? What'd you find? In the binder?
Yeah.
I will tell you guys, your Q2's kind of screwy. I got all kinds of random pages. It is what it is. Copier went weird on me. Actually, I feel that maybe should have right. First, I'm doing it. See, I've got a whole thing going here. I'm gonna put all y'all's stickers on here. I got some Baylor. I got me a Hollins one with a donut. Woohoo! That's what I do. Start sticking in here. Awesome, James. Thank you. You're so cool. I love this. That's the best. All right. We got a big night hopper at the top, right? Awesome. Yeah. Yeah, forgive the weirdness if you got lots of screens copying, you have extra pages and things, make sure you have readout available, but just kind of ran off here. You'll be good though. Yes, sir. They'll be on teachers, so when you go to teachers, the homework will be in there for you. So there won't be, yeah, it'll be a page for you, all the other ones you have supposed to be, we just had to make it print. Oh. But that's you can do that. So, online anyway.
Hussy hush.
Excuse me?
Oh, I know, you know the bug. You know how to write it. Thank you. Okay, so you said, leave around. Oh.
Wacky sound.
Oh, I don't know, y'all were all pretty wacky today, I loved it. He's so spoiled, look at this.
I'll do this
Spoiled,
too.
rotten.
One of those stupid.
No shame.
My girls, you can like sit, like you can make him sit like in you and he's like on your lap.
Oh, yeah, with the legs out, the French bulldog, they do that. Oh my gosh, one of my professors from college, she has this like, some mutt, probably has some German Shepherd and I don't know what else, but the dog's name is Carson, and her ears are permanently up, and they lean in and cross each other like this. And her ears are like that in every picture, it's just the way they are, it's hilarious, they're big too, they're not little ears. This dog is spoiled. Nobody loves you. Nobody loves you, Oswald.
I love
Spoiled.
Yeah, the same we have the Texas Healer.
Oh, wow. One big guy, one little guy, huh?
He's like, oh my
Goodness, Haji. You're a silly boy. He'll follow wherever I know he's got. Yeah,
You get bonus points to winning me.
everybody got bonus. Everybody got as many bonuses you could get. Everybody got today because y'all all did it. I'm so excited. Great.
Was it actually me and the 5 star?
Love it. Fabulously. Look. Yes, you did. You all got them. You want to see something super interesting? Then you want to have a interesting. But this is a volunteer book for number 26 that I done today. And it's very interesting the way they write stuff. Each of the girls is useful. They tell you where they live and what they do. And the cool thing is, like, ones that were a man, actually, it looks a lot. I wonder how many houses still there. Just so they're wrestling below and staying. Yeah. It's as full as it's gonna get, I think. It's full. That's really
Okay, I want them.
Because actually has some bananas. There's actually a thing here. I'm all about it. Those are our easy. Did you roll that all? No. The change is really like when you put the seed, you have a party, you have to, you got to really get one. So but it's only there. Have a club, that like stuff. And during prohibition, the alcohol was never in the that came up with all I have to treat because that's what I need help on didn't happen here. Oh, are you attacking me, right? But he's kind of like there's a cemetery that probably every walk up and yeah. And go hello. Go.
You can use this and that for now.
eBay is really old. Interesting. Comment. I didn't hear today. It's not today.
74, that's not good.
Yours. No. No.
Where's one?
Yeah, here's the 1921. So this one's the older one. I think this is the one with the chafing dish stuff in it. Cracks me up. Very interesting.
Older. Wow. Yeah. Yeah, it's not overfilled. I just have to get the points out. If you look at that little space, and I'll show you if you can see how it works, but this little space here. Let me see. I think you have it. But actually, tell me when we get out of the That's good money, you don't want that. You want to read that? Here you are. Oh, did you? Canadian coins. Get them all? Almost? You know, alright. I put it hot back on the group again.
Got any cows in there?
Yes.
Oh, yeah, I forgot about. Oh, wait, no, oh, you're in your own. That's how you do it.
Figured out?
I was trying to spell hello, but I was spelling it H-E-L-L-S.
Oh, that's not alone. We could try.
Yeah. I didn't even.
Oh.
Right.
Banana. Somebody tried to in my cradle. No good. Oh, no. Yeah. Nice. Hold on.
One, I really feel one.
No, no candy doll, hey, that on your cancer. Yeah, stay, yeah, but come on, excuse me, sir. Good boy. Boy, yeah, good boy, hello. Hello. You're not gonna say hello? You usually do. Yes, sir. For what now? You got a random skittle? That's funny. What'd you say, you said? Or you just, who's talking to me? You? Yeah? I don't like that. It's beautiful though, isn't it? It's like a cracker. I didn't do these guys, I bought these. One for the living room, with these scale and follow the tail on the red side. What's this? That is big. And my grandfather purchased it with his first paycheck. Well, okay. Right. It still works, it sure is. You have to turn it on, and warm up, and it takes time. Yeah, it still works. So you can, this is the kind you can like, it's shortwaves with like hand radio almost. You can pick up all kinds of weird things, but it still works. Speakers work. Okay. Well, if you do the ham radio, I don't know if this is trouble, but like the ham radio guys, they can like off the stage. Yeah, they can hear people in different continents, go Australia. This one takes a while. Here you go. Yeah. It does work the minute.
No. Yeah.
There's a wall here. It's Jackie. Senora Jackie. She's good fun. There, I bet the one. Go.
Used to have eyebrows.
Oh, I did, at one point, huh? Yeah. Senior Squish, it's very sad. Poor Senior Squish. Still, I always do that.